Welcome to the class of electrochemistry. In our last lecture, we learned about Nernst equation. Okay. So, it is basically relating this cell potential and the reaction quotient, that is the ratio of the logarithm of the ratio of the concentration of the right hand side constituent and the left hand side of a reaction. Okay. So, we would just learn some of the applications of this Nernst equation in connection with electrochemistry. Okay. So, basically Nernst equation is this. Now, application means either you find out this one or you find out this one experimentally, and while finding out these quantities you would be able to know some other information with respect to the reaction under investigation. Now, let us first have a look at this solubility, means whether we can find out the solubility and solubility product of this sparingly soluble salt like silver chloride. So, when you try to dissolve silver chloride solid, then it will not be soluble. It appears that it is not at all soluble, like sodium chloride. If you add sodium chloride to water, that is regular salt, then it is completely getting solubilized in water. It is soluble in water, completely soluble, but this one is not soluble. So, what happens that when you add silver chloride crystals in water, it produces a saturated solution of silver chloride, where the whatever amount of silver chloride that goes into solution will have this will happen through this equilibrium Ag plus and Cl minus. So, is it possible to find out this solubility equilibrium, I mean information about the solubility equilibrium, that is the equilibrium constant of this process, or can we find out Ksp, that is the solubility product, or in turn can we find out the solubility S of this sparingly soluble salt? So, answer is that yes, it is possible to find out the solubility product of this sparingly soluble salt in water by the application of Nernst equation. So, first of all we have to, as I mentioned in the earlier class, that we have to have the appropriate cell that is constructed, which is having the net reaction like this. Then it is possible to find out the equilibrium constant of this process from this cell potential measurements. Okay. So, let us have a look at two reactions. One is AgCl plus electron, that gets you Ag plus Cl minus, and its corresponding electrode half cell presentation is AgCl solid Cl minus Ag. And if we look at another reaction Ag plus electron, that gets you Ag solid, okay, and its corresponding representation is Ag plus Ag. So, now if we subtract these two reactions, I mean up to this, what are you going to get? We will be getting AgCl to give you Ag plus Cl minus. Okay. So, to get you this, so basically we get the same reaction as this one, because this is the equation that is involved for this particular quantity. So, therefore, let us construct a cell having this overall cell reaction. Therefore, the half cells will be this one and that one. Okay. So, half cell potentials, that is the standard reduction potential for this one is phi 0 is equal to 0.22 and here phi 0 is equal to 0.80. Okay. So, therefore, what are you going to get? So, therefore, if we combine these two, therefore, cell will be like this, Ag plus Cl minus, then it will be Ag plus or better you write like this, Cl minus AgCl Ag. Okay. So, therefore, you have Ag plus, this is one half cell, this is another half cell. Okay. So, therefore, let me write it. So, therefore, the net reaction AgCl giving rise to Ag plus Cl minus, it will be Ag plus, then Cl minus AgCl Ag. Okay. So, therefore, your equilibrium constant for this process, I mean for this one will be K equilibrium is equal to, in terms of activity, it will be activity of Ag plus activity of Cl minus divided by activity of AgCl. Okay. And since this is a solid, therefore, you can, for all practical purpose, you can replace this with unity. So, therefore, this activity product of these two will be, so therefore, K is equal to activity of Ag plus activity of Cl minus. So, it is called the activity product, and for dilute solution, you can replace, of course, it is a dilute solution because solubility is known to be low, therefore, the corresponding concentration is very low. So, therefore, you can for all practical purpose you can replace this with concentration of Ag plus into concentration of Cl minus, and that gets you Ksp. Okay. So, basically concentration of Ag plus is equal to concentration of Cl minus is equal to C. Therefore, Ksp is equal to C square. So, if we can find out this value of C, then we should be able to find out the value of Ksp. So, therefore, let us turn our attention to the cell. So, E0 cell of the above reaction is, so at equilibrium, since it is an equilibrium. So, at equilibrium the cell potential will be 0, because equilibrium means delta G equal to 0. That means you have minus NFE. So, therefore, this will be equal to 0. So, therefore, we can write that at equilibrium your cell potential is equal to 0. So, therefore, E 0 cell will be equal to phi right 0 minus phi left 0, and phi right 0 is 0.22, phi left 0 is minus 0.88, that gets you minus 0.58 volt. Okay. So, therefore, the way it is represented is not a spontaneous process, rather this will be the spontaneous direction. Okay. So, therefore, Ag plus and Cl minus will combine with each other to form solid AgCl, and it will precipitate out of the solution. Therefore, we can write from Nernst equation that delta G 0 is equal to minus delta G 0 is equal to N F E 0, which is equal to R T ln K equilibrium, because at equilibrium the cell is not producing any electricity, because E is equal to 0. So, therefore, this is equal to this, therefore, we can find out, therefore, basically from E 0 using this part we can write that K equilibrium is equal to, or ln K equilibrium is equal to N F E naught divided by R T, and ultimately if you calculate with appropriate numbers, then you will be getting that K S P is equal to about 1.6 into 10 to the power minus 10. Okay. So, this is your solubility product, and solubility will be basically square root of this. Solubility will come out to be approximately like 1.3 into 10 to the power minus 5 moles per liter. So, therefore, it is basically, so whenever you would like to find out some information about the chemical reaction, like say for example, here we have discussed this determination of solubility and solubility product of the sparingly soluble salt using this EMF method, then you need to construct the right electrochemical cell, and then if it is a solubility equilibrium, then it is an equilibrium process. So, at equilibrium cell potential will be equal to 0, because delta G at equilibrium is 0. So, therefore, cell potential equal to 0 means if you plug in 0 for the left hand side on this Nernst equation, like this one, if you put 0 for this, then E cell is equal to R T by N F ln Q R, and then this Q R at equilibrium is basically K equilibrium. Okay. It is the reaction quotient at any time, at any condition, and at equilibrium this quotient becomes K equilibrium. Okay. So, therefore, basically this expression comes, and therefore, from this expression you will be able to find out this solubility and solubility product of the sparingly soluble salt. So, this is one important application of Nernst equation. Next is another important application of Nernst equation could be the potentiometric titration. Potentiometric titration. Potentiometric titration means you titrate like a general titration, and during titration you measure the potential that is a cell potential, that is the cell potential. That means, you construct a cell, and within that cell, maybe in one of the two half cells, you carry out some titration reaction, and as a result of addition of your titer, what happens that the concentration of the reactant is getting affected or getting changed as a result of dropwise addition of your titer. Okay. So, we can follow we can follow a reaction like this, say Fe 2 plus Ce 4 plus, that gets you Fe 3 plus Ce steric Serras system. Okay. So, the corresponding constructed cell could be like this: Pt solid, Fe 2, Fe 3, because it will be a mixture of Fe 2 and Fe 3, then a reference electrode. It may be a standard hydrogen electrode or maybe something else, like maybe calomel electrode, mercury mercurous chloride, mercurous chloride reversible with respect to chloride. So, depending on the concentration of this chloride, whether it is a decinormal or it is a normal calomel electrode, this is calomel, normal calomel electrode, or it is a saturated calomel electrode, the potential will be accordingly varied. Now, depending on which one you are choosing, whether this calomel electrode or something else, accordingly this reference electrode potential will have to be considered. So, therefore, basically cell cell potential or the electrode potential for this will follow a trend, and it will change like potential phi equal to phi naught minus 0.059 log concentration of this Fe 3 divided by concentration of Fe 2. Okay. So, therefore, if you plot this potential against say saturated calomel electrode, it will follow a trend like this. So, this may be regarded as an equivalence point. So, electrode potential and number of drops of this cerium that is added, okay, steric system that is added. So, added titer in ml. So, this way you can follow a potential follow the potential of the cell, and by which you can find out the equivalence point for this one. So, this is another important application of this EMF measurement. Third application could be like determination of this pH of the medium. Now, pH of the medium means you would like to find out the acidity of the medium. So, by EMF you can also find out by EMF method you can also find out the pH of the medium. pH is basically negative logarithm of activity of hydrogen ion. It is a dimensionless quantity. So, for all practical purposes, for dilute solution, you can replace this with minus log of concentration of H plus, provided the concentration is not high enough. Okay. So, how to find out the pH of the solution? Okay. So, pH of the solution means you would like to find out the concentration of H plus. That means you need to look for one half cell which is reversible with respect to H plus. That means the potential, electrode potential of that particular half cell will depend on the concentration of the H plus present there. Okay. So, therefore, simplest case will be platinum solid, then H2 gas 1 bar, then HCl maybe 1 molar, then 1 molar or even even a different value, maybe activity of H plus, let us write. Then the reference electrode. Okay. So, that means you can find out the pH of this particular solution. Even if there is no HCl, suppose your unknown solution, you want to find, still you want to find out the HCl, I mean H plus concentration, then you need to form a hydrogen reversible H plus reversible electrode there. Okay. So, therefore, E cell will be equal to phi right minus phi left. So, phi right means phi reference or standard something minus phi left. Okay. So, basically this is equal to E cell equal to phi reference minus phi H. So, therefore, phi reference minus phi 0 H plus R T by F ln activity of H plus. Okay. So, therefore, what you can write? You can write that this is equal to. So, therefore, activity of H plus, and ultimately you can replace this with minus phi 0 H for all for all the pressures at 298 Kelvin, maybe 298 Kelvin at any pressure, any 1 atmosphere pressure at all the temperatures, it is assumed to be 0, because in this case the condition is that you need to have your pressure kept at 1 bar. Okay. Then minus R T by F ln concentration of H plus. So, therefore, E cell. So, this is 0. So, therefore, phi reference minus R T by F ln C H plus. So, this phi reference is known, this will be estimated experimentally. So, therefore, plugging in the respective values like value of R, then temperature, then value of Faraday, you will be able to find out, the concentration of H plus. Once concentration of H plus is known, then you should be able to find out the pH of the medium. So, this is one example. Nowadays various types of hydrogen proton reversible electrodes are there. Okay. Like another is this quinone hydroquinone system. Quinone hydroquinone system, where quinone is this, then plus 2 electron plus 2 H plus, this gets you hydroquinone. It gets you hydroquinone, okay. So, this is Q, this is QH2. So, this is also H plus reversible. So, you can also make a H plus reversible electrode half cell like PT solid H2 Q or QH2, then Q, then H plus, activity of H plus, and then maybe a standard electrode like maybe saturated calomel electrode or maybe reference electrode. Okay. So, basically its potential, you can also you can also get the corresponding expression for E cell involving Q and H2Q. E cell is equal to E0 cell plus this, and in the same way that we have estimated the value of pH for this standard hydrogen electrode, we can also make use of this quinone hydroquinone electrode for finding out the pH of the unknown solution. Nowadays, glass electrodes are used for for this determination of pH of the medium, where glass electrode is nothing but it is a special kind of glass coating on a bulb, where where basically this the equilibrium is established across the membrane with respect to the proton, and the potential will also potential of this electrode will depend on the outside H plus ion concentration. So, I do not want to go into the details of this glass electrode, but nowadays this commercial pH meters have this glass electrode. Okay, so this is another this is another example of this pH determination, but for this particular quinone hydroquinone, it has got it has got some limitation that beyond certain pH you won't be able to determine the electrode potential very accurately. So, therefore, there is some restriction on this. Anyway, so this finishes the application part of this electrode application part of the electrode potential. Now, next we will have some example. We will have some example. I mean, at least one more example of this application of conductometric titration. So, because we have not given enough example of this particular thing. So, let us have at least one example of let us have at least one example of this another example of this conductometric titration. Now, conductometric titration means it is basically you are measuring. So, it is an application of conductance measurement. So, one example or one application I already have explained to you to find out this degree of dissociation, that is lambda m by lambda m 0. From this value you can find out the degree of dissociation of weak electrolyte, because for weak electrolyte direct determination of these quantities through graphical extrapolation was not possible. Now, in conductometric titration you have a solution like you do a regular this indicator titration, that you add titer from with the help of a burette, and with the help of a pipette you pipette out a definite amount of the alicot and put it in the beaker, either in the beaker or in the conical flask, and then you add some indicator and do your indicator titration by progressive addition of your titer from your burette, and you make a note of how much of the burette material has been added to the beaker, and based on that you using the formula V 1 S 1 equal to V 2 S 2 or similar, you find out the strength of your unknown material. Now, in conductometric titration, what you do, that you have your beaker and say you have your acid solution like HCl solution. So, HCl is here, and you dip your conductivity cell having 2 electrodes, its cell constant is also known. Okay. Then you measure the conductance. Okay. So, what you do, you measure conductance as a function of added titer. Here your titer is, because it is an acid based titration, HCl plus OH minus, that gives you H2O plus Cl minus. Okay. Cl minus, if it is NaOH, then you will have plus Na plus. So, this will continue until all the H plus ions are exhausted, and beyond this equivalence point there will be some excess of OH minus and Na plus depending on how much excess you have added. Okay. So, you are adding from top with the help of a burette drop wise this alkali solution, and you measure conductance of the solution, that is this is Siemens, okay. And then this is your volume of alkali, okay. So, you will be noticing that the conductance will reduce to a minimum point, and then after that it will rise steeply. It is like that. And this point corresponds to the equivalence point or the end point. Okay. So, what is exactly happening over here? Why conductance of the solution is increasing, but for your information, one thing that you should always keep in mind, that in case of conductometric titration, the titer that you add from outside using a burette, it should be more concentrated, at least maybe 10 times more concentrated than whatever you take over here. But in case of regular acid base titration, the trend is reversed, that you take a concentrated solution over here of your unknown material, and then you add from outside with the help of a burette 10 times dilute solution in order to find out the exact end point through indicator titration. Okay. So, why it is like that? Because if you add a more diluted solution compared to this one, then the solution will be more dilute when you add titer from outside. So, because of this dilution, there may suffer an additional change in conductance due to dilution, okay, because there is already a change in conductance due to the fact that this H plus ions are removed and H plus ions are replaced by Na plus ion. Okay. So, that is why this titer is kept at a higher concentration. Okay. So, therefore, what is happening, why this is happening, why it is happening like this? Because you see that initially you have H plus Cl minus. So, its molar conductance of H plus is very high, about 400 Siemens centimeter square mole inverse. These are less, about 70 or something like that. Okay. Even for sodium it is much less. So, when you add OH minus from outside, these ions are removed, okay, and these ions, this H plus is removed and it is replaced by less conducting sodium plus. So, therefore, what happens that you are replacing 400 with something close to, say, for example, 70. So, there is a drop due to replacement of 400 with a 70. So, that is why it keeps on decreasing like this, and this decrease will reach an extremum point, okay, because extreme point means no further reduction or no further removal of H plus by OH minus is there when the equivalence point is reached. Okay. So, at equilibrium, at equivalence point, so all the H plus ions are exhausted and it is replaced with sodium ion, and H plus is converted to water. Okay. So, beyond this equivalence point you have some excess of OH minus, and OH minus is also having high molar conductance, and that is close to around say 200. Okay. So, again it is after reaching this minima, again it starts to increase steeply, but this slope will be not that steep compared to this slope, because the mobility, I mean because this conductivity of H plus ion is almost double that of this OH minus. So, this way you can find out the equivalence point of an acid base reaction by means of conductometric titration. So, you can do similar experiments, like you can also do a precipitation titration. Okay. So, in that case precipitation titration means, say for example, AgNO3 plus say KCl. So, AgCl precipitate will be formed. So, you can also follow this precipitation titration with the help of this conductometric method, but only thing is that you need to titrate with a stronger solution or a concentrated solution to minimize the effect of increase of volume due to addition of the titer. Okay. So, this is one simple example of this conductometric titration. So, this is the second example that I have given to you. Next is, now let us try to find out Gibbs free energy change and cell potential. So, how to find out the relation between, although we have already written the expression that delta G is equal to minus NFE, but can you reach that? Okay. So, can we deduce that expression? Okay. So, delta G and E cell, delta G and E cell. Now, idea is that when some amount of charge Q, okay, so that moves through a potential difference delta E, potential difference delta E. Okay. Then work done, okay, work done by the system, work done will be equal to minus Q into delta E. Okay. So, delta E is equal to 0 is greater than 0 for galvanic cell. That means when galvanic cell delta E is equal to 0, so the reaction is spontaneous. Now, let us write the expression like G is equal to H minus T s, then G is equal to U plus P v minus T s at constant T temperature and pressure. Okay. So, this is the usual case for electrochemical cells. Okay. Electrochemical cells, we can write delta G is equal to delta U plus P delta V minus T delta S. Now, delta U is equal to Q plus W. So, this work, total work is equal to the mechanical work PV work and non-mechanical work, especially for electrochemical cell, it is the electrical work plus electrical work. Okay. So, we can write here minus P delta V plus W E L electrical. So, therefore, we can write delta U is equal to your Q plus W electrical minus P delta V. So, if we plug in this information over there over this expression, we will come up to delta G is equal to Q plus W electrical minus P delta V plus P delta V minus T delta S, and that gets you Q plus W electrical minus T delta S. Okay. So, if the condition of reversibility means that if we do not draw much electricity from this, that means when the drawn current goes to 0, that is limiting condition when I goes to 0, then we can write that under limiting condition for galvanic cell, Q is equal to Q reversible is equal to T delta S. So, therefore, if we plug in this information, then we come up with that delta G is equal to W electrical. So, and W electrical is equal to minus Q into delta E. Okay. And Q delta E is nothing but minus N F delta E. So, therefore, delta G is equal to minus N F E. Okay. So, therefore, delta G is nothing but the delta G, this delta G is nothing but the delta G of the process that is involved over there, and this is the chemical reaction. So, therefore, it is delta G of the reaction, because delta G reaction is nothing but the net electrical work. So, therefore, delta G reaction is minus N F E. So, that is why that is how this relation can be relooked at. Okay. So, therefore, this is the relation between the change in Gibbs free energy and the relation between the change in Gibbs free energy and this delta E. Delta E means it is the cell potential, or it is the electromotive force. Okay. So, from we can find out other thermodynamic parameters, thermodynamic quantities from this electrochemical measurements, but right now we do not want to concentrate onto that. Now, next is an important thing that we have talked about this Daniell cell. Okay. Daniell cell. So, Daniell cell means you have zinc sulphate half cell, zinc sulphate zinc, you have copper sulphate copper, you have a salt bridge, okay, and you have like this one, that is plus, this is minus. So, you can connect this with an external wire, so that electron will flow in this direction and current will flow in the other direction. Okay. Now, so what is the net reaction? Net reaction is that zinc will get solubilized. So, zinc plus copper sulphate whole net cell reaction, zinc sulphate plus copper deposited. So, this is the normal trend, and normal trend means this is the spontaneous process, because in this direction if you go, then delta G will be less than 0. So, this is the this is the natural direction of the process. Okay. So, it is an electrochemical cell. So, what happens that now if we attach this with, say for example, an external source like this, external source like just remove this one, just remove this one, and then just you attach this side with this variable resistance, and you make such that when maybe this external potential difference is either external is potential is maybe less than 1.1 volt or equal to 1.1 volt. These are the two situations. So, if it is less than 1.1 volt, that means the external force, external electrical potential is less than this, means normal reaction will take place. Now, when external electricity, that is the potential difference from the external source, if it is equal to 1.1 volt, then no reaction is taking place. But if the situation is such that if your external potential difference is greater than 1.1 volt, that means you are now biasing this electrode with a negative potential and this electrode with a positive potential. Then what will happen? Then electrons will flow in this direction and current will flow in the other direction, because originally if this biasing was not there, then current would have flowed from this direction, this to this, and electrons will flow from here to here. But if it is reversely biased like this with this one, then current will flow in the other direction. Okay. So that means you are biasing the reaction or electrodes in such a way that this normal reaction has been reversed. That is, in that case copper will dissolve over here and zinc will be deposited. So, basically reverse process will take place. So, what happens in case of an electrolytic cell? So, therefore, basically electrolysis will take place, that the reverse process is going on. So, originally it was a galvanic cell, that is a Daniell cell, but if you do this modification that I have just explained to you, then the reverse will be the situation, that the zinc will be deposited and copper will be dissolved, and so electrolysis will take place. Electrolysis will take place. That means the internal reaction, original reaction, this reaction will be surmounted by the electrolysis of the process, where zinc sulphate will become zinc and copper will become copper sulphate. So, basically this is this is going to happen. Okay. So, therefore, let us try to look at what will happen when we supply electricity through a say for example aqueous solution, containing some electrolyte. So, say for example, let us take example that electrolysis of water. Okay. So, water, so you have two electrodes. In case of electrolysis, you have two electrodes. One is cathode, okay, and another is anode. Okay. So, therefore, cathode means reduction, anode means oxidation will take place. Cathode, anode, and we are supplying a DC source. That means, it is a steady current is provided through this acid solution. That is, you have pure water and maybe you are putting 1 or 2 drops of HCl to it, and then you will just look at what is going to happen. So, what will happen? That you will have redox process in the, and complementary redox processes will take place in two electrodes. One is your cathode, another is your anode. Okay. So, basically you have this production of hydrogen gas at cathode and production of oxygen gas at anode. Okay. So, cathode means reduction, okay. That means H plus electron, that gets you half H 2, and your OH minus or maybe H 2O, okay, OH minus, or maybe better to say H 2O, 2 H 2O plus twice electron, that gets you basically the whole reaction is H 2O minus it gets you reduction like this. So, from water you can also have this H 2 gas plus 2 OH minus, okay. And whenever you consider oxidation or maybe say other thing, then H 2O. So, for this one you can write H 2O will get you half O 2 plus 2 H plus 2 electrons. So, either this one, maybe you can think of this one or that reaction depending on the pH of the medium, and also this anode reaction. So, these two are for cathode and this is for your anode reaction. So, that the net reaction will be like 3 H 2O gets you H 2 gas plus, or better to write not in that way, H 2 gas plus half O 2 gas. Okay. So, this is the net electrolysis process, that in your at cathode you have hydrogen, at anode you have oxygen. Probably you remember that we have discussed one point while measuring the conductivity of a solution, okay, or conductance of a solution. In that case you need to have two electrodes, that is your cell. You dip that cell in your electrolytic solution or the solution containing electrolytes, and then with the help of a device, I mean like this Wheatstone bridge principle, you can find out the resistance of the unknown arm, provided the bridge is balanced. But in that case we have talked about one thing, that we have to use AC instead of DC. Why AC instead of DC? Because if you supply DC, then whatever I was discussing over here, this is going to happen. So, this is going to happen means the cathode and anode, these two electrodes will be covered with hydrogen and oxygen, and the electrode characteristics will be affected. So, that is why if you have AC, then once this will be cathode, this will be anode. So, hydrogen and oxygen will be produced like this. In the other half cycle, this becomes anode and this becomes cathode. So, therefore, here at cathode your hydrogen will be produced, although in the earlier half cycle, oxygen was equivalent amount of oxygen was produced. So, therefore, this electrode and this electrode will have the hydrogen and oxygen deposit, I mean hydrogen oxygen liberated in the vicinity of these electrodes. Now, if this electrode is platinized, is coated with finely divided platinum, then what will happen? It will induce the combination of hydrogen and oxygen to produce water. So, this way this complication in the process will be removed. So, basically that is why AC is used over there, and for electrolysis is very important in the industry, that by means of electrolysis you can produce this alkali metals like molten sodium chloride. If you electrolyze, then sodium will be produced, and so and also maybe sodium hydroxide production, that also can be carried out with the help of electrolysis process. But only thing is that some parameters are to be adjusted accordingly, so that you can get the desired product. Now, when it is the question of electrolysis, then there comes two laws by Faraday. So, one is Faraday's first law. It states that the weight of the substance formed at an electrode during electrolysis, it is directly proportional to the quantity of electricity that is passed through the solution. That is, amount of electricity that you are passing, if you increase the amount of electricity, it will increase the amount of material that is deposited. And the other one is the weight of the different substances formed on the passage of same amount of electricity. In that case, it is in the ratio of their equivalent weights. So, this will take up will be taken up in the next lecture. So, what we have learned in this particular piece of lecture, that some applications like measurement of pH, then solubility product, then potentiometric titration for the this EMF measurement, and for conductometric titration we have just talked about how this conductometric titration can be used to follow the titration process. And then we started with this electrolysis, I mean discussing electrolysis process, where we have started with this electrolysis of water, and just we have stated this Faraday's law. So, we will take this up in the next class with a little more detail, and then we will move on to some other topics that that are required to be discussed. So, till then, thank you.